Okay, so today we spent some time working on the Brett Schneider curve and how to predict significant wave height. And remember, significant wave height is the average of the largest 1/3 of waves. So that's kind of an important value to know. But we're talking about wave height in general. Now, wave height, as you would hopefully expect, is directly related to wave energy, which means the more energy is transferred due to fetch, duration, and wind speed, the bigger the waves are going to be. Now, the average height in the ocean is like 2 meters or less, which is only about 6 feet. So waves generally are not that big. On really turbulent days, you can see white caps. We see them even out in the bay. And that's when we get that height to wavelength ratio called critical steepness, and they begin to break right there without even coming ashore. Now, we've hopefully you've heard of the Sanford-Simpson scale, which tells us hurricane intensity. Before we could actually accurately measure wind speed perfectly, Sir Francis Beaufort came up with the Beaufort wind scale, and it describes the appearance of sea surface and draws a correlation to wind speed. This table's in the book. It's 8.1 or 8.3, I think, depending on which version of the book you have. And in a general sort of way, it approximates what's going on in the ocean to the wind speed. So on a typical day, like we have around here, we tend to be in the 2 range, let's say, where we get small wavelets, crests, glassy appearance, stuff like that. We don't generally get 0s or 1s. And right up to, say, Beaufort number of 4, we will still get the boat out, things like that. You'll see down here we have hurricane. Air is filled with foam and spray, sea completely white. That's what it would seem like if you were out at sea with wind speeds over 73 miles per hour. The Beaufort wind scale is useful because it allows you to classify the seas based on the wind speed, as well as estimate wind speeds based on the appearance of the sea. This graph's kind of an important one. This one is also in the book, and it is a sort of amalgamation of satellite data. We'll talk about Jason and Topex Poseidon a little later in the chapter. But this is sort of global wave heights, where the reddish colors are very large waves, generally 5 meters or more. That's about 15 feet. And blue is the more average, which is around 2 meters, and going all the way down to purple, which would be much smaller. There's sort of an imaginary line going across, especially the southern hemisphere. Let's draw the equator in. Be kind of right about here. That's a little high. And they call this area, at about 40 degrees lat, the roaring 40s. And then we would get the ferocious 50s and the screaming 60s right along the edge. You don't have to actually know those names. What happens here is we get a whole lot of very large waves. And why do you think that might be? Well, think about it. What are the factors that affect wave height? Wind speed. It's not going to be any faster, particularly south in the southern hemisphere at those latitudes in the northern. Wind duration. The wind's going to blow as long as it blows, north or south of the equator. But the last one, fetch, is different when you're in the southern hemisphere. If you notice up here in the northern hemisphere, we have all of this land mass. There's not a lot of land mass down here. There's a very large area of open water, and that gives very large fetches. So the reason why the waves get so large in the Southern Ocean, particularly south of Australia, is not for any other reason except that there's a very large fetch there. And if you ever get the chance to go down there, you will see a couple graduates are going there this winter. This is a picture that's also in the book. It's of the USS Ramapo. Now, before this happened, before the USS Ramapo went out in 1933, around 1900, the U.S. Navy kind of came up with what they call the 60-foot rule. And the 60-foot rule basically said that if you thought you saw a wave over 60 feet, you were full of baloney. They didn't think it was mathematically possible. In 1933, the USS Ramapo was out and about. It was traveling with the waves, which means it was kind of steering into the waves. And the waves were kind of going this way. Oh, see, it's already on the diagram. And the boat's going in the same direction. What happened was there was a guy standing up here, and they know the exact height of the crow's nest. And he was able to accurately take a picture, as a matter of fact, of the crest of the wave being at perfect eye level to the crow's nest. Do a little trigonometry, which I'm sure is everybody's favorite. They were able to actually estimate the height of the wave. That's one of the ways we still measure waves, not just satellites, but also through using a little geometry. That wave that the USS Ramapo encountered was 112 feet high, which is pretty freaking big. As a matter of fact, it's the largest wave on record still, almost closing in on 80 years later, that was measured directly this way as opposed to any other way. There are rumors of bigger waves. If you ever saw the movie The Perfect Storm, there were people who believe those waves were topping 150 feet. But those were not accurately measured. Those are just accounts. So when we were talking about significant wave height, we were talking about the highest 1/3 of waves. This has to do with seas. Now remember, seas are the place where the waves are generated from the storm. A fully developed sea has this very important definition, which we'll put right here, which is it's the maximum wave height that can exist due to the conditions, the fetch, the speed, the duration, so on and so forth. The reason why they can't continue to get bigger as more and more wind blows is because energy is lost when the waves break. Remember, they reach that critical steepness and they begin to break. And the energy lost is equal to the energy that would be gained from wind blowing on it again. So there's a point at which the wave just cannot get any bigger based on the conditions. Now, in terms of significant wave height, we can use significant wave height, like from the Brett-Schneider curve, to predict how big the highest 10% of waves are. You can also do average. We will do some problems on both of these tomorrow in class, so make sure you write these down and pay attention to these formulas. So seas are the area where the storm is and the waves are being generated. As soon as the waves move away from the site that they're generated, they become swell. Swell is uniform, they're symmetrical. They sort of sort themselves out based on their wavelength. So the waves that have all the same wavelength frequently have the same period, and they sort of become very uniform and symmetrical. And if you were to draw that typical sine curve, as it moves away from the storm, that would be considered swell. The energy that's transferred, these things actually move away from the storm, frequently very far ahead of the storm, because they travel faster than the wind. And out in the open ocean, they can travel very long distances without losing much energy. Swell becomes really important. Surfers like, quote unquote, swell. Swell are waves that come from storms. Eventually they hit the coast and become surf. But surfers like them because they have very orderly patterns to the breaking. This idea of a wave train, I'll draw it on the board for you tomorrow. There is a picture in the book and it'll be on the next slide. Wave train is a group of waves with similar characteristics. They tend to have same wave height, same wavelength, same wave period, and they move away. These are if you imagine dropping the pebble in the pond, as the ripples move away from where you drop the pebble, they form wave trains where they're all basically the same distance apart, same height, so on. Over time, that leading wave disappears and it's replaced by another wave that was generated and catches up to it. So these are called wave trains. In this formula, where group velocity is equal to 1/2 wave speed, I'll draw a picture on the board tomorrow for you to see how that works. And finally, there's decay distance. It's the distance over which waves begin to break down. And it's usually several hundred kilometers away from the storm. This picture is of wave trains, and the basic idea is that A, B, C, and D here are over time. So, the storm would be blowing, there's a storm, and it's blowing, and the waves are moving away. Remember, they have to move several hundred kilometers away. And here we have 4 waves. Over time, this first wave is gone. It begins to die down. It gets very flat. Instead of being big, it begins to get flat. But at about the same rate that wave is dying out, next wave is catching up to it. So you tend to have the same number of waves traveling along in these packets at the same speed in the same period. And because the first wave is disappearing at the same speed as the next wave is catching up to it, we say that the speed is equal to 1/2 the speed of an individual wave. I'll show you that with an example in real life. We'll do this tomorrow in class. We're going to stop right there.